This mini lecture will discuss the molecule that is emitted in a flatulating cow. This molecule is called methane. We will also discuss ethane, ethene, and ethyne. The topics we will cover are the molecular geometries, valence bond theory, and the hybridization of atomic orbitals, as well as the hybridization in molecules when they have more than single bonds, namely double and triple bonds, such as in ethene and ethyne. Let's begin with methane. Methane has 1 carbon and 4 hydrogens. These bonds are all single bonds, also referred to as sigma bonds. The geometry is aligned as a tetrahedron. It has a carbon in its center, and then on each corner of a tetrahedron is a hydrogen. The angle in a tetrahedron is 109.5. Let's have a look how the hybridization works. We know that carbon has 4 valence electrons. Looking at the electronic configuration of carbon then, we have to fill the 2s shell with 2 electrons and then the p shells with each filled with 1 electron for a total of 4. Now, in order to get the carbon to be able to have 4 bonds, as seen here, we have to promote one of the electrons from the 2s shell into the empty 2p orbital, which leads us to this diagram. However, looking at methane, you can tell that all these bonds are completely the same. That means they all have to have the same energy. If this bonding orbital were true, then this would be having a different energy than these 3 bonds. So we can't do that. So what we have to do to solve this problem is to hybridize these atomic orbitals. And in order to hybridize these, we will throw them all together in one pot, stir them all up, and then we have sp3 hybrids, 4 of them, because there's 1 s and 3 p's that were all mixed. Now we have orbitals available, all on the same energy level, all filled with 1 electron that are now available for bonding with each of these hydrogens. So, looking at how this works is looking at this diagram. There's a carbon, the carbon in the center with the 4 sp3 hybridized orbital. Then you add your 4 hydrogens to the bond, and these hydrogen electrons here are all in sigma orbitals. Yeah, they're all in the s shell. And these are now approaching these sp3 hybridized orbitals to actually make the molecule. Let's look at ethane. Ethane has 2 carbons and 6 hydrogens. Like methane on the slide before, they're all single bonds or sigma bonds. So ethane, each carbon is also tetrahedral with a bond angle of about 109.4, leading to the tetrahedron. Now that means that all of these sigma bonds here from the carbons are once again sp3 hybridized. And the hydrogen comes in with their s orbitals. Looking at this space-filling diagram, in the center here you see carbon with 4 sp3 hybrids, and the hydrogens are in the spherical s orbital. Now let's discuss how we will introduce the double bonds. Ethene has 2 carbons with 1 sigma bond and 1 pi bond, the double bond. However, there's also a sigma bond here and here and here and here. So carbon has 3 sigma bonds. This one, and that one. It has not 1 pi bond as well. That's the double bond. So let's have a look. Since there is carbon with 3 electronic densities, 3 sigma bonds, that carbon must be sp2 hybridized, leaving 1 p orbital available for bonding. So here's the carbon, and the 3 sp2 hybrids are right here. The orbital that is then responsible for the double bond is this p orbital. Hydrogens come in and bond for the sigma bonds as here, and then these 2 p orbitals right here, those red and blue dumbbell-shaped orbitals will overlap here to form the pi bond, which is the double bond. Looking at the geometry, the bond angle between this carbon-hydrogen bond and the carbon-carbon bond is 121.3. That leads to the fact that this is a trigonal shape, so it is a flat molecule. Finally, ethine. Ethine has a triple bond. That means the carbon here has one sigma bond to this carbon and two pi bonds. Over here another sigma bond. Since carbon is connected to two sigma bonds, this carbon must be sp hybridized, one s and one p, leaving two p orbitals to make these pi bonds. Looking at this diagram, here's your carbon representing this carbon, and here's that carbon representing that carbon. The orange spheres here are the sp hybrids. These come together now to make the sigma bond between the carbon and the carbon. Hydrogens again in the s orbital coming in together, making the sigma bond to the carbons, which are right here, these two. Then how do we form the pi bonds? Just like we did in ethene on the previous slide, this p orbital here, the dumbbell-shaped orbital, blue and red, they overlap to make one pi bond. While the other one here, this yellow and the purple, they are lying perpendicular exactly 90 degrees to this p orbital, and they form the second pi bond. Looking at the geometry, you can see that the angle between this sigma bond and this triple bond, which one of them is sigma, is 180 degrees. So that means that this molecule is linear in shape. Finally, let's have a look of what type of forces are occurring in between molecules. First of all, hydrogen bonding. Hydrogen bonding occurs between hydrogen and the elements of fluorine, oxygen, and nitrogen. Here's an example of water. Water has an oxygen that has a partial negative charge due to its electronegativity. Hydrogen has a partial positive charge because most of the electrons are being pulled towards the electronegative element. So now this negative end of water on oxygen is going to interact via hydrogen bonding with a positively charged hydrogen on the oxygen. The next intermolecular force is the dipole-dipole bonding. The dipole-dipole bonding means that when there's a dipole in a molecule, like here in HCl, the delta negative of the chlorine will interact with the delta positive of the hydrogen. Dispersion forces are instantaneous dipole moments in molecules that can always change as the molecules swim around. So here is a dipole moment that is positive interacting with another molecule that has an instant dipole moment where this is negative. Finally, the ion-dipole interactions are occurring between an ion, such as in this one, the sodium cation, and here is a dipole from water, delta negative. Now you learned molecular orbital theory and the intermolecular interaction. Therefore, you should be able to explain the fact that cow forts are flammable. Think about it.